Right, people, don't know what you use, but I'm dying to get to a hairdresser, actually. But anyway, right, we're going to a quick look at strain and Poisson's ratio. Poisson ratio, Frenchman, went about in the 19th century. And I'm going to look at the strain. See if you stretch something, see like a rubber band, you stretch it, it's going to have a strain induced, not just in this plane, but in this plane and that plane. That one going that way and this one going that way. Imagine a rubber band, it would get smaller as you strain it or pull it apart or elongate it or whatever. The same thing would happen if you compress a material, it will stretch that way and that way. So we're going to look at how we figure that out, and that's Poisson. He figured it out. So we're going to have a look at that, okay? Right, let's see now. We're going to have a look at that in a wee while, Macaulay's. Right, so we've got some sort of block, like that. And we'll call this like the X plane. And if you have a kind of stretching like that, say, in that direction, this is going to make this elongate. I don't know if that looks very good. But what happens is, the thing is, this part here will have a strain as well, and we'll call this the Y direction, and it will have a strain induced in this, which would be your Z direction. So we're saying we've got X, Y and Z, like that. Yeah, I don't know if you can really see that, it's marginally better drawn. So you can see that if you have this L here, or say this length, we'll say that's like the length Y, X, sorry, this is X going across here, X like it is there. You're going to have a stretching, a change in length in this direction, and a change in length in this direction. And also it's going to contract in this direction. Notice here it's like slightly smaller there, probably better seeing it there. So in the Y direction there's going to be a change in Y and a change in Y here. This will be negative because it's actually, the change will be negative because it's getting smaller. You see that, it's getting smaller. And also in the Z direction there is going to be a change in Z and a change in Z on that side, if you imagine. And also see if you get an overall change in length. Say this change in length, you had the original shape there and you stretch it, you're going to say the change in length is going to be divided equally at each end. So the change in length here is going to be the change in length over 2, the change in length here will be the change in length, oops, that should be bloody X, sorry, a change in length X, and change in length X over 2. Very bad drawing. I'll maybe try and write that out a wee bit better. We have a length here, length X, length Y, length Z. When we stretch this out, so when this stretches out, it's going to make this longer, but it's going to contract this in the way, and each, if we're looking at just one side of this, the amount that stretches out there will be the change in length divided by 2, because the other half of it will be coming out this way. And the same here, this bit here, is going to stretch or get squashed in the way. And again, that's going to be delta LZ over 2, and it's going to get squashed like, or pulled down the way. And this is this plane here. So again, we've got your X, Y and Z planes there. Right, we know that the strain is equal to the change in length over the length. Now looking at this here, the strain in the x direction, the change in length x over the length x, change in y direction, delta Ly over Ly, and again the strain in z direction. So it's just basically this sort of simple strain equation we looked at before, except we're looking at it in all directions now and how it affects the whole shape of the material. Now materials that are we call isentropic, it means the kind of the strain is equal in all directions, and this depends on the type of material it is and if it's uniform, and if it has flaws or whatever would affect this. But that is the stress in this direction is the stress in this direction. But what happens is the amount of stress in the y and the z directions is equal in this for an isentropic material. So you can say that the stress in y equals the stress in z, or the strain. Sorry, the strain. So we can say, well, the ratio of, and the y and the z, they are not the Young's, but the ratio of longitudinal to lateral, which is equal, the strain on the lateral strain here. These are lateral strains, they're called them, and this is a longitudinal this way, and your lateral is that way. So the ratio of these strains is a kind of constant that it kind of determines how it reacts under compression and tensile stresses, and it's really useful when you're looking especially at beams and things. Say for instance Eiffel Tower, you'd want to know whatever stress is on these beams, how they're going to react, etc. And this constant is called Poisson's ratio, and denoted by this kind of symbol here, nu, as in Greek, lowercase n, right? And that's basically the negative lateral strain divided by longitudinal strain. Remember, as that gets smaller. So say for instance this ratio comes out at 0.3. What that would mean is if you had a 10% stretching in your longitudinal directions, you would have a 3% stretching in the lateral dimensions, dimensions. And for this to work, it has to be in the elastic region. It has to follow Hooke's law. So in other words, it has to stay in its elastic region, and once you go to the plastic or it starts to deform, it becomes far more complicated. And so let's have a look. See, once you do all the figures for certain materials, you test them out and stuff, and it gives you values for this Poisson's ratio. you have Poisson's ratio range from -1 to 0 to 0.5. Some examples here. Looking from the region between 0 and 0.5, you would have cork 0. That's got quite a special property, as well as here up by rubber, which will have one at 0.5. Most materials you'll find are somewhere in between. Cork actually doesn't, see there's 0, what that 0 means, it doesn't actually have any lateral strain when you apply a longitudinal strain to it. So if you think about, see that's your kind of bottle top, if you've got a cork and you need to compress it into there, there's like, it doesn't stretch in that direction or get contracted or whatever, or get pushed if you're trying to squash that into there. So it's much easier to get that into the bottle and seal it. And we'll talk about rubber in a wee second, I'll pull what the 0.5 means. And most metals are around about 0.3, got cheese there, 0.45, and concrete. So you get a smaller lateral strain depending if this gets smaller. Obviously it gets bigger. Right, now, and these are materials that generally are in nature. These, if you get any materials coming along to this -1 here, that is, they're in a region where if you compress a block or something, it's going to get smaller longitudinally, but it will also get smaller, oops, can't see that, in the lateral directions as well. It seems kind of odd or counterintuitive. You'll find these are kind of man-made materials, special kind of foams and things, and if they align the crystals or the lattice structures and things, or whatever it is, to kind of create this situation. And what we've been looking at here, we're actually just looking at as if you have one applied stress in one direction, i.e. longitudinally there. And you'll find from that the strain created in these lateral directions would be the strain of y is equal to minus Poisson's ratio times the strain in the longitudinal part. Again, the strain in the z direction is minus Poisson's ratio. Remember, because that's getting smaller, that's why that's negative in comparison to the x. Hope you can see that, and that's making sense. So the strain in the y direction is equal to this minus Poisson's ratio because it's getting smaller. See, if that was, well, I've got, if that's compressing, that would actually be getting bigger. Or if it's pulling away, that would be getting smaller. So that's why you have this negative, because it's always opposite to the longitudinal. And now that only applies though if we have a longitudinal stress in one direction. And remember Young's modulus, stress over strain. So if we want to look at the strain, say in the x direction, we're going to have to think about the stress in the x divided by the Young's modulus of the material. Right, but this only works if you've got longitudinal, a longitudinal stress. Whereas if you have also lateral stresses, we have to take that into account. So by doing so, we can say the strain over Young's modulus at x on the x axis minus Poisson's ratio times the stress in the y direction, y lateral directions, minus the stress incurred, that should be like that, in the z directions. Mind, they're not 6's, they're supposed to be sigma. Right, now we can fill about with that. So strain x is equal to 1 over Young's modulus times stress x minus, we can take the common factor out here of Poisson's ratio, so stress at y plus the stress in x. And again, for the stress in the y direction, 1 over e, and it's just the stress of the z minus Poisson's ratio, stress in y, sorry, away with it, stress in x plus the stress in the z, just the same as that one, basically, just looking at the different angles there. So obviously the, sorry, that should be z there, for God's sake, that should be z there. And again, looking at the strain on the z axis, it's going to be so what's happening there is we're looking to find the strain in the x direction, we're looking at the stress, then we're subtracting Poisson's ratio times the sum of the stresses in the lateral directions in reference. So this one here, you could say the y-axis was your reference axis, and you're looking at the stress at this axis and subtracting Poisson's ratio times the sum of the stresses in the other axes. And again, exact same for the z direction, the z axis. We're doing the same thing, we're looking at the stress in the z axis and subtracting the sum of the stresses times Poisson's ratio to find the strain at z. So what this does, this kind of encapsulates applying Hooke's law and Poisson's ratio to a material in all directions if there's stresses on it. So now we can calculate more complex stresses, and as I say, in all 3D events. This is called the, it's actually called the generalized Hooke's law. Right, so one thing that's what's useful for this is quite, if you think about, if you're looking at the strain for the length of say x, you would say, you'd look at the ex and we'd apply that equation we did there. These equations, right, see if we sum all these equations up, you can sum them all. And what would that give you then? That would give you the change in volume. So, and see if you plug all the equations into that. I'll not need to go into that, but what happens is you get this volumetric strain of 1 minus 2 Poisson's ratio over Young's modulus times the stress of x plus the stress of y plus the stress at z. Now what happens, see if you look at this here, see what if this Poisson's ratio equals 0.5. This 1 here, 1 minus 2 times 0.5 going to equal 0, so this is going to all equal 0. If we've got a Poisson's, a material is a Poisson's ratio of 0.5, what it means is it doesn't change volume. And we've come across this many times in fluids and things where a fluid like water is seen as incompressible. So when a material has a Poisson's ratio of 0.5, it's incompressible. And yeah, the volume remains constant. And obviously this is very handy looking at oils and stuff for hydraulics. You don't want any compressibility. When you put a certain flow on one end, you want the exact same flow at the other end, or the same amount of flow. And it might be going at different speeds, what have you, or be under different pressure. But really that's it. That's all there is to it really. We've just been looking at compressibility or stretchability of material, how it stretches or compresses in its lateral directions due to a stress in its longitudinal direction. That's where we get the Poisson's ratio from. And if you think about in 3D, if you've got stress coming in all directions, you can use that to work out the strain, and you can take into account the lateral strains as well, and also the volume. If you think about it, if you take into account all the lengths and just multiply them, you'll get the volume, or the strains anyway, the change in lengths. You can use that to determine the volume, and using that equations we kind of worked out. And also, as I said, at 0.5, that's when you get incompressibility, which we need that in, say, hydraulic systems and where we're using pumps and things. You need to deliver a certain displacement of fluid or whatever. You need to have that incompressibility in the fluid or it won't work properly. Okay, and what I'll do is I'm going to do tutorial videos associated with each subject we're looking at, such as this one and Macaulay's and whatever else we need to do, and more circle, that'll be coming up soon, don't worry about that. Right, thanks for listening, speak soon, bye.